We've had quite a few of these sessions now. I think everybody in the room is pretty familiar with this set of slides. So today for our extra session, we're just going to offer some time for additional lightning talks or updated lightning talks. Or if somebody would just like to give a more free-form project pitch, they can do that as well. And then we'll have a little bit of time left over for discussing projects and for getting help with teaming. Who might be interested in doing a lightning talk today? All right, so we've got Pete. Anybody else interested in talking? I think then in the interest of time, we'll go ahead and get started with Pete. So Pete, you have the floor. I will turn the screen share over to you. Again, shoot for about 5 minutes, but if you're the only one going today, we've got a little bit of flexible time here.
So I'd like to talk about the B cells and germinal centers, specifically the adaptive immune system response. So the goal of a B cell is to be able to develop the right antibody that will counteract whatever foreign antigen has come into the body. So when that happens, you start out with some kind of antigen presenting cell that gives a naive B cell that antigen. And then the B cell has to develop the right DNA code that will eventually allow it to be able to produce the correct antibody. So how that happens goes on inside of a germinal center. So this is a diagram of one such, and let me get a laser pointer here. You start out with an activated B cell that has just been given an antigen, and it enters a dark zone, which is the left half. Then it starts to divide rapidly and undergo a process called somatic hypermutation. So what that means is every time it divides, it's going to do a random DNA modification. And at the same time, that antigen has to be split between the two daughter cells. So you're going to lose a little bit over time. Now, there's going to be anywhere from 2 to 6 of these random divisions. And then our B cells are going to lose the ability to stay in this area and start migrating over to the light zone. Now, in the light zone, the B cell's goal is ultimately to talk to a T cell. A T cell is the red guy here. So what it has to do is hold in one hand a receptor, the antigen, and in the other hand, it has to have the antibody. So by interacting with the T cell gives the B cell some survival signals that would then either allow it to re-enter the dark zone, or if it fails to receive help at all, then it may undergo apoptosis. So what that means is if you have some B cells that are not very successful and they do not have a very good antibody, then they should die off. Now, at the same time, you also have these FDCs, follicular dendritic cells, and those are going to help replenish the amount of antigen to the B cells. So our B cell is going to go back and forth between these two zones. And this is what I'm trying to model. Ultimately, you want to have either a plasma cell or a memory cell coming out of this. And when it does, it exits my simulation, which would be the lymph node. I'm only going to be focusing on that part of the tissue. So here's another diagram of the same germinal center. This one's just rendered a little differently. There are 2 chemical gradients in separating the 2 halves. One is called CXCL12 and the other is 13. And those are just going to help the B cell migrate between those 2 zones. And they're going to be secreted by some background cells, stromal cells and FDCs, follicular dendritics. Now, when it comes to evaluating the viability of an antibody, there's several different approaches out there for doing that. So the T cell, which is the T cell receptor, and the B cell receptor are going to be compared to each other. And one approach out there is just taking the Hamming distance between those two. So let's say I will represent my antibody as just 2 integers, for instance, make it really small and simple. In that case, then you just have like an exponential and it will blow up a bit if you have a successful antibody. There are some other approaches out there that I'm considering as well, as one of them is more focused on randomization. So the hypothesis I'm considering is that when a B cell enters that light zone, which is the right half, then it has to pick up some more of the antigen in order to restore its supply. If it runs out of antigen, then it may undergo apoptosis because it's no longer able to compare with the antibody and interact with the T cell. So I'm thinking that if it has this very successful antibody, then it's able to pick up more of the antigen, and a greater amount of antigen will allow it to reproduce more in the dark zone. So that, in other words, the amount of antigen picked up will help it divide more and be more successful. At the same time, I'm also hypothesizing that if a B cell fails to interact with the T cell at all, maybe just because there are a lot of cells around or another B cells taking up the slots in the contact area, then it will die off, even though it may otherwise be a highly successful B cell. So here I've highlighted a few things that I would like to get out of this model. One of the most clear objectives I could set is just how many plasma cells do I get, or how many B cells with max affinity to the antigen do I have? So that can be tracked with the counter, though another way, which is the third approach, is tracking the average or overall affinity across all the B cells. And I've seen that quite a few times in the literature, so it'll allow me to, establish a benchmark. And finally, I want to measure how the apoptosis rate is correlated with the amount of time needed to get to the output cell. So if there's a lot of apoptosis rates, then a very successful B cell might die off. And then lastly, I want to mention that one of the reasons behind developing a spatial model is so that we can track the amount of B cells that are interacting with T cells, and there's a limit to that. So here, I've highlighted 2 different varieties of B cells. In the interest of time, I may only focus on one of these and just treat them as the same type of B cell, but really a B cell cycles between these 2 subtypes essentially as it migrates between those 2 zones. So the first one is on the dark zone, the central blast, and it divides a number of times. It lives in the dark zone because it has a specific receptor that brings it over there. And it also undergoes asymmetric division and somatic hypermutation, which I discussed earlier. Now, on the other hand, a central site is what happens when a central blast loses its division capacity because it has divided enough times. It'll start migrating over to the light zone, and then it wants to talk to a TFH cell, or T cell that is follicular helper. So lastly, I've brought up a few references. One of them is a primary paper that has a lot of information I'm going to be looking off of. And another one has the basic theory behind it, which is leave through the dark zone. And finally, I have a few more papers here for biological background. So that's all. Thank you.
All right, thanks, Pete. James, did you have any comments? And then we'll have comments from everybody else too.
No, I think that's a great topic. I mean, I think we had people last year. Well, we had a presentation on antigen refinement in the lymph nodes, and there was also a hackathon group that was trying to work on thymus. So I think trying to think about this kind of problem is very appropriate for CompuCell. The trick is always, but it's not a reason not to do it, of course, is that the issue about how antigen recognition works. But I think using a random string and matching is probably as good as any. That seems to work. That'll be what people do. So I think it's a very exciting project. I hope people will be able to join you and help out with that.
Yeah, I just found out from Joel yesterday that the team did it last year. So now my next step is to look into that old recording.
I think we may have access to some of their project too. I can get in touch with them and find out if they'd be willing to share it with you.
That's a good idea.
All right. Well, thank you, Pete. Anybody have any questions or comments for Pete before we move on? Anybody interested in his project that might want to join the group?
Maybe if Pete puts his email in the chat so people can reach out if they are interested in joining the project.
Yep. Good. And Pete, also, when you get a chance, I think I saw you, did you add it to the shared teaming document? I think I saw you put it in there yesterday. Oh yeah, that's right. That's where I saw it. Yeah, so Pete, if you want to add your project to the shared teaming document too, and just give it a description on one of the extra pages, and that'll help people who are interested contact you as well. All right, so did anybody else want to present about their project today? Ultimate, you said you had an updated version. All right, well, if you'd like to go next. Giving you unmute privileges there.
Hi, everybody. Good morning and good evening. Just I want to check my voice because I doing with the computer. I don't want to. Just 1 second. Yeah. Okay. We actually uploaded a new version for our project. You can see it in our shared folder. That's the reason I wanted to talk today. Yesterday, after the breakout sessions during the hackathon time, we met with Melanie and Lampros and AFFINITY, and we 4 of us had able to had chat this morning, and we had some more ideas, and we wanted to update our ideas, and we come up with a new title, and we come up with new kind of observations and problems we would like to talk about it. By the way, we also updated the Word document about the hackathon. We included the observations, aims, and a little bit methodology. So if people are interested, you can get in touch with us, and I can also share my screen. Is there any problem about my voice?
No.
Nope.
Okay. Okay. Do you see my screen?
Yes.
Thank you. So from the beginning, I would love to work on I had this main problem in my mind, like Turing type of pattern formations and modeling the reaction diffusion systems using this compusal 3D environment. And I was wondering what kind of, because reaction diffusion systems are very popular and it's used in a lot of applications. And one good application is the Schneckenberg model, well-known Schneckenberg model. We also discussed about it, and it's an example of Turing type of patterns, and it's well-studied area. It has really nice conditions for Turing type of patterns. And it was our starting point, actually. And yesterday with Melanie and others, you can see the names here. We had some chat, and we could say that we can also try to explore the digits kind of patterning, because there is a stripe type of patterning in this case. And we asked that question: can we simulate? Can we look at can we track the pattern formation on the CompuCell. And the yeah, we have the initial paper here. We also put this slide in the teaming shared folder. In our shared folder, you can see it. In this article, the mathematical model is well described. The domain is well described. There is also the domain growth issue in this article, and yeah, the activator and inhibitor mechanism is well described in this model. And so we have the idea for Turing systems, Turing type of patterns to be able to emerge. We should have the paradigm like the inhibitor should diffuse much faster than the activator, long range inhibition, short range activation. So this kind of situation condition also occurs in this case. So we would also allow to explore the details of this digit development. So here you can see the emergence of pattern formation during the development. And there are also other examples from literature. I already mentioned about these things. And I quickly passed through the mathematical model. This is the Schneckenberg model. It's with equations in the form of partial differential equations with zero flux boundary conditions. Here are the diffusion operator we can see, and the rest of the parameters represents the reaction kinetics. And about this model, again, this long range inhibition and short range activation is necessary point, is a requirement for patterns to emerge. So that's why we should have the main diffusion coefficient larger than 1. So we don't want that they diffuse in the equal rate. That's the idea behind it. So yeah, this is for the Schneckenberg model, mathematical model, and I also want to, yeah, this is the flow chart for the new model. That is the model for digit development. So it's like we have this BPM, R, and FGF. These are our parameters, and this R here stands for an inhibitor, and FGF stands for the activator. There is this mechanism, and I'm sure biologically someone else can explain it much better in our group. I want to pass quickly through the mathematical model, and this is the general form of the model, but non-dimensional form of the model is also described in this paper, the same paper that we took it here, and it's very similar to the Schneckenberg model. And this is also, you can also see it in this picture, well describe the process to be able to track the development. And this is the, actually, this is the improvement that we have done so far. And if you are interested to join our group, we would love to hear it. And we, of course, we are open to any suggestions from the organizers. Thank you very much.
So I guess what I'm trying to, you've got a lot of possibilities there, all of which are very interesting. And so my question is really about how to try to maybe make this a little more focused so that it's something you can do. Are you thinking that each person in the group will do a different model? Is that how you're thinking about it?
We haven't done that much sharing yet, but we thought that if we could able to find something related with Schneckenberg model, we thought that with the new kinetics with the digit development, we could able to do a similar analysis in CompuCell so that we can get that model. And we also wanted to continue after the hackathon. If 2 days is not enough, we would really love to continue on this project.
So, but I'm trying to understand what are you trying to do? In other words, if you're running, if what you're trying to do is run a reaction diffusion model here, for example, I don't remember if this was actually published with CompuCell or whether it's just there's a subversion of the Schnackenberg. I know this is the one I've got. So is that
Exactly.
so this is a typical model that you would have. Now, in reality, in biology, you almost never have reaction diffusion. What you have are chemicals that diffuse in the environment, and then the cells make decisions based on the environment. And so one thing that one can do is start with a reaction diffusion model like this, and then gradually replace the reaction terms in the model with cell behaviors. And that makes it much more realistic. That would be a possibility. There are certainly, there's nothing wrong in a weekend in building models of the kind that you showed. In other words, that one that for the digit growth is something one could easily implement in a few hours. Putting it into a growing domain may be a little bit more difficult or interesting, and so you'd have to explore how that worked. So yes, there are a lot of possibilities that you could explore. I'm not sure. So I'm sorry about that. I've got to just see the participants. Okay. I think this is a great project. There's a lot of possibilities. But what I am trying to think about maybe is what we could do to focus this. In other words, pick one example to begin with, for example, or ask the question, how do you cellularize it, or what are the particular questions that you want to start with? Because you've raised so many different questions. It's a lot to do. So let's see. There's a comment in the chat from Melanie. If we can influence a bunch of cells to elongate mass on a striped field, which would represent chemical diffusion, simulating limb development, that's a possibility. As I say, the one that I'm familiar with recently, which is there's this nice reaction diffusion model of stripe formation in zebrafish by Alexandria Volkaning. And I worked with some students last semester who converted that to a cellular model. So in that case, you have the cells that appear or disappear, or in this case, appear or differentiate or die based on chemical fields. They secrete chemicals themselves, which influence their neighbors. That's something you can do. You can have cells migrate in response to the chemical fields, which certainly occurs in development. You can have cells differentiate with response to chemical fields. That also occurs in development. It's a little bit different in different situations. In the limb bud, you have some migration and some differentiation during development. And so those are all possibilities. And I'm happy to maybe meet with you before Saturday morning to review these. But I think really you need to decide where to start. Getting familiar with how the reaction diffusion solver in CompuCell works isn't a bad place. That's a good thing to learn. So you might want to try simply to start with. You could try just implementing that limb bud model that you have. Just typing it into CompuCell, seeing if it runs. Let me share the that Schnackenberg code, because I can put it. I'll put it into a demos folder for module 8.E. Okay, so you can download that.
Thanks
Right.
so much. Yeah, actually, our group also has some ideas, and they also. Lampros, would you like to take it over?
Yeah, sure. Hello.
Thank you so much.
Thank you. So our initial approach, for now at least, is to set a realistic goal for the first day, maybe the first hours, and try to emulate the spot formation at first with the reaction diffusion model. And after managing that, we'd like to try to create the stripes. And if we manage to do this in the first day, we will try for the digit formation in the second, trying to adapt that, the Schnackenberg model to the other we have, I don't remember the name.
Digit patterning.
So, yeah. So our initial approach, at least for now, is this. And some thoughts are on perhaps creating some simple simulations of the single cells of what we want to achieve, to see what compartments they might have, what behaviors. And after that, perhaps fusing the two basic models we have. Of course, any input on that would be great. That's a.
I think those are great. I think that's a great plan. So I did put those simulations in the chat in the demos folder for here. I haven't looked at those simulations in quite a while. I was just trying to run one that sounded like it might be interesting, but I'm not sure what it does. So I have to, but there are a couple of demos. There's a Schnackenberg, a Fitzhugh Nagumo, and a Geiger-Meinhardt model that work. There's something called cellular Schnackenberg, which doesn't seem to work. So that one, I don't know. I don't know what that one is doing. As I say, these are fairly old, but they may give you a little bit of guidance to start with.
Thank you. Yes, we'll definitely promote it.
But I think it would be great. I think that reaction diffusion is a great system, and coupling it to cell behaviors is great. Either, as you said, elongation, chemotaxis, differentiation, proliferation, death. You can model all of these things. There's an old paper. There's an old paper that we did. Let me find it for you.
James, I'm so sorry. You mentioned a paper about zebrafish modeling, Alexandria. I was looking at that paper. Can you also, is it possible to write the author's name if you can?
I'm sorry, Pedro is saying something in the chat. Pedro, do you want to tell us more on this?
Yeah, so basically, you, for example, do you remember the angiogenesis model?
Yes.
So there was a set of equations, and when you translate those equations to CompuCell, you you are inspired by the equations, and you translate the behaviors into an agent-based model. So you actually don't solve any of those equations at all, except for the fields, the diffusive fields, right? So that's more or less the idea that James was saying, and that I agree a lot, which is you guys inspired by these equations, instead of working with the solver only, you try to translate these behaviors in an agent-based model to achieve the same result. So it's possible for you to reproduce the same patterns without even using the reaction diffusion solver. And
Yes,
this will justify the use of CC3D. Yeah, that's it.
what we were thinking of was having, for example, the actuator and the inhibitor as two fields, two chemical fields. Having CC3D have the diffusion, and then have each cell have an uptake for each of the chemical fields, processing them inside with antimony, and then ejecting them back.
That's perfect. Yeah, that sounds perfect.
You can probably get away with hard coding what happens inside the cells to begin with and not putting it in antimony. Much as I don't generally encourage people to do that, I would, to start with, it's easier to just hand code the functional forms in Python. And then you can translate them into antimony. It's easy to do the other too, but it's one extra step in developing. So that's great. I'm looking, let me try to find that one old paper that was, I'm still, give me a second.
Sorry for chipping in, Pedro. Yeah, I was just listening to your idea. You mean that not dealing with the PDEs in antimony, we can use the biological process to have the same results? Is that what you meant?
Yes. So, for example, instead of having field A generating field B, which is a typical process of a reaction diffusion system, you can make a cell sense field A, and based on the concentration of field A, the cell secretes field B. So this is the biological process behind the reaction diffusion equation that is actually a simplification of what is happening in the biology. So yeah, that's the idea. I hope it's clear now.
Yeah, and the way you do implement that, I mentioned this before, as I say, we really need a module to cover it, is you start out with a reaction diffusion equation. You put cells down. You have the cells read the chemical field and secrete not the actual field, but a tracking field that mimics it. And then you adjust the cell behaviors until they reproduce the actual field, the fields from the reaction diffusion equation. And then you take the reaction diffusion equation out, and then you just have the cells. And so you can, it's a little bit like learning how to bicycle with training wheels. You start out with the training wheels on, and then you gradually remove them. And you replace more and more of the responsibility for the dynamics with things that actually happen in biology. Because again, it's not that chemical reactions never occur in the environment, in tissues. There are chemical reactions, but most patterning doesn't happen through reaction diffusion. It's the fact that the cells are, in a sense, simulating a reaction diffusion equation. Diffusion definitely happens, absolutely. Although a lot of things that we think of as diffusion are actually contact mechanisms, like the ones that Giulio was showing you yesterday, because the interaction ranges for diffusion are very short. But yes, these are great places. But start with learning how to use reaction diffusion in CompuCell, and then we can talk about how to substitute cells.
Hi, I'm Melanie. I was just wondering, is it possible for cells to secrete chemicals? Like, can we simulate that?
Well, yes, we covered that the other day, last week, actually. Right, it's secretion module is very usual in CompuCell, yes. And
That's
so
my fault.
What you would do is you have diffusion, you have chemical, if you're going to do reaction diffusion, you have two chemicals that diffuse. And the question is how much chemical is secreted and what the cell types are that are doing the secretion. And so you control inside the cell the decision about how much you secrete based on the concentration of the two chemicals. And that implements a reaction diffusion equation without actually having a reaction.
Yeah, okay, yeah, that makes sense. Yeah, okay, that's possible. It seems like.
Oh, absolutely. It's definitely, and that's a good project, and it's quite practical to do.
I believe that's all from us for now. Thank you so much. And we have a lot of papers to look at.
Yeah, thank you very much.
I mean, I'm
Thank
sure we
you.
can find more too, but those couple are a place to start.
Thank you so
Thank
much.
you.
Are there other comments? Hayden, do you want to continue?
Well, next thing was just to ask if anybody else wanted a chance to talk with James or Pedro or any of the instructional staff about their project. We probably only got about 10 minutes left, so we're probably not going to do breakout rooms because it'd probably take the whole 10 minutes just to get set up. But if anybody wants to spend the next 10 minutes asking questions about the project, please let us know in the chat or raise your hand, and we can actually, James, do you just want to give everybody on mute?
Actually, everybody has unmute privileges.
Okay. So everybody should be able to mute at this point.
So are we doing breakout rooms now or not?
No, we've only got 10 minutes. James only has about 5. So anybody that needs to ask
Oh.
James some questions within the next 5 minutes, you might want to do so now. Yes, so Shalai, the idea behind agent-based modeling is that you have objects in your simulation that have properties and features, and you kind of let those objects go to interact, as opposed to a more mechanistic model where every single, portion of the simulation is governed by, so like molecular dynamics would be very mechanistic because it's governed by force field calculations of each atom against each other. Agent-based, each agent is interacting with each other within the simulation. That's kind of a brief overview. Maybe Pedro or James would have more to say about that, but that's the agent-based modeling is a little bit of a broad term. But that's kind of the base idea.
Agent-based model means that you have a model which has things that do things that are discrete objects that do things. The model could be cells interacting in a tissue, as opposed to a continuous field, which is the density of cells, where the cells are not represented explicitly. Cars in driving around in the environment, rather than, so anytime you use densities instead of representing the individuals, then you're not in the agent-based world. Of course, you can mix things. We have agent-based cells, but we don't have agent-based chemical fields. So that's the fundamental choice. Do you represent space? Do you represent things as continuous densities, or do you represent them as individuals?
Yeah, Sharon has a good explanation there that you're modeling micro components and governing their behavior and kind of letting the behavior of the system emerge, as opposed to just trying to simulate the entire system at once. But yeah, agent-based modeling is it's a big topic right now. And so like I think the definition varies from field to field a little bit and even from group to group. So it's one of those things that's a little bit hard to nail down sometimes.